But the good news is that you already know most of it. So it either goes back from 234, organic 1, or things that we've done in previous chapters in this semester. So there are 2 or 3 new reactions, some very important ones, but a lot of this should be reviewed to you. And that's always a good thing, right? Aldehydes and ketones. In carbonyl compounds, this next section of the book is going to deal with carbonyl compounds. We're going to do aldehydes and ketones today. Remember, aldehydes have a hydrogen attached. Ketones, we have 2 carbon-based things. The next chapter, we're going to do carboxylic acids. I think esters are in there too. And then we're going to do carboxylic acid derivatives and acyl transfer, where we'll hit these other guys. We always start off with a little bit of simple nomenclature. When you are naming an aldehyde or a ketone, parent chain must contain the carbonyl. Okay, so when you're identifying your parent, you look for a chain containing the carbonyl. We're going to drop the E from the end of the alkane, replace it with al for an aldehyde, and an ONE for a ketone. If you look at ethanol here, now this is acetaldehyde. Everybody in the world knows it as acetaldehyde, but it is a 2-carbon parent, therefore it's an F. It is fully saturated, so it's an ethane. An stands for alkane, the ending alkane, and al because it's an aldehyde. Again, our longest chain here is a pro. We have a 2-methyl on it. It's an alkane, and it's an aldehyde. Acetone, 3-carbon chain. In carbon number 2, we have the ketone. Same sort of thing here. Have a bute for a chain. It's saturated. It's a ketone in 2, a methyl in 3. Any questions? When we have a substituent that's either an aldehyde or a ketone, so this is somebody else's parent, okay? Somebody else's parent. Here we have a hexanal, so that's this chain here. But we have a ketone down here in carbon 5. We indicate that as a 5-oxo group. Oxo stands for carbonyl, ketone carbonyl, here in carbon 5. If we have a cycloalkane or a benzene ring, those will be parents of their own. Okay, so the cycloalkane is the parent, and the aldehyde hanging off is a substituent. For that, we use carbaldehyde, cyclohexane carbaldehyde, 2 words. Benzene carbaldehyde, everyone knows this as benzaldehyde, and benzaldehyde is a fine IUPAC that's recognized. In fact, if we had substituents here, we would name this as a derivative of benzaldehyde. Standard rules, we're looking for first point of difference. Here we have a cyclohexene. Now, up to this point, we would have started numbering at the alkene and gone through it. But here, the carbonyl is highest priority, so it's going to be carbon 1. If it's carbon 1, that means that our double bond is down here in carbon 3. Cyclohexene only. We show that it's an alkene with an EN, drop the E, not E-N-E, just like we did for the alkane. AN for alkane, EN for alkene. Naming this as a derivative of benzaldehyde, this would be a 3-nitro, This is a very simple straight chain. This is a 2-hexanone. Again, the "an" refers to alkane. And here I stuck a double bond in it. So this is going to be a 4-hexene 2-one. Here's our parent, 4-hexene 2-one. If we have carbonyl as a substituent, we're going to call that an acyl group. Common acyl groups, acetyl is basically an ethanoyl, is the proper name. Formyl would be methanoyl, 1 carbon. And this is benzoyl. Benzoyl peroxide, you've probably heard of that. Acne stuff and whatever. This is the side chain. Now we're not going to do a whole lot of nomenclature, but let's just look at some simple examples. Go ahead and work on these and give me some IUPAC names. Remember, our parent here has to contain the carbonyl. So our parent is going to be the little side chain hanging off.
Oh, whenever there's a carbonyl, we're not going to use a benzyl parent.
Right. So here's our 3-carbon chain. That's a probe. We're going to shoot for the lowest number, first point of difference. So we let this guy be carbon 1. And our benzene ring is simply a phenyl substituent. 1 phenyl, 2 propanol. Our parent here is going to be the cyclohexane. That means we have a carbaldehyde and a methyl. Alphabetically, we're going to let the carbaldehyde be carbon 1. So this is going to be a 1 carbaldehyde, 3 methyl, and they are on the same side of the ring plane, so they are cis. I forgot to put cis out here. I should have. Here we have 2 aldehydes. Our parent is 1, 2, 3, 4, 5 carbons. Now, because they're aldehydes, by definition, they must be at the end of the carbon chain, right? They must. Therefore, you don't have to number this. We simply have to say it's a pentane and it's a dial. Here we have to decide on who's going to be our parent. We're going to take this guy with the double bond in it because that makes it a 1, 2, 3, 4, 5, a pentene. It's a 1-al. So it's a, here's our parent chain. It's the carbon 1. Carbonyl takes preference over the alkene. We have a 4-pentene, al. Again, you don't have to say where the al is, because it must be at the end of the chain. And here we have an ethyl group at carbon 1, 2, 3. 3 ethyl, 4 pentene al. Now again, we will see a little bit of nomenclature on your next exam, but it's not going to be anything overwhelming, certainly nothing even this complicated. Any questions? Nomenclature is important because we have to be able to communicate with each other, to say what we're looking at and what the compounds are. But nomenclature in the second part of organic really becomes secondary because we have so many reactions that we have to deal with. All right, a little bit about carbonyl compounds. Again, this is an sp squared carbon. This is a carbon-oxygen double bond. Because it is sp squared, we have about 120-degree bond angles all the way around. It's planar, of course. Remember, we have 2 pairs of electrons here, but they are sticking out in the plane of the board, here and here, as opposed to coming up. Going way back to 234, one of the very first ways that we made carbonyl compounds was by the simple ozonolysis of an alkene. Remember, when you do this, you're simply going to split the alkene. The mechanism involves the formation of an ozonide. Basically, ozone adds to the pi system. When it adds to the pi system, you form this cyclic thing like this. It's very unstable. The ozonide then decomposes. When it does, in the presence of zinc and acid, reductive cleavage here, we wind up with 2 carbonyl compounds. Again, all you're doing is taking your double bond, you're splitting it, and making each carbon a carbonyl. You make both aldehydes and ketones, depending on what's attached. Any questions? Once again, if we have a substituted in the presence of ozone followed by zinc, we will get ketones. We can also do this if we have a substituted alkene with permanganate. Permanganated acid, again going back to 234, we said would split a carbon-carbon double bond right down the middle. In this case, again, we would generate 2 ketones. You must remember, however, that you can't do this if we have a hydrogen, because in the presence of permanganate, aldehydes are very rapidly oxidized to carboxylic acids. So this works to make ketones. Ozone works to make both ketones and aldehydes. Any questions? Probably the next reaction we learned that gave us carbonyl compounds was a simple hydration of an alkyne. Now, to do the hydration of an alkyne, we had to use mercury 2 as a catalyst. Mercury 2 attaches to the pi system here. We get Markovnikov addition of water. In this case, we form an enol intermediate. Now, in a chapter or two, we're going to do a lot of enol chemistry. Remember, an enol is always in equilibrium with the ketone. This spontaneously will convert, make a double bond here, pick up a hydrogen out here, and we make the carbonyl. Once again, in chapter 21, I believe, we will do a whole lot with the equilibrium between an enol and its carbonyl compound. The reason we're going to do that is, as this thing collapses, we actually develop a negative charge here, don't we? That's why it picks up a proton. What we're going to do is use that negative charge as a nucleophile. But that's later. Simple hydration in the presence of mercury. We can also do this using hydroboration oxidation. Now remember, hydroboration, unlike the mercury catalyzed hydration, gives anti-Markovnikov regiochemistry. So the enol that we form here, the hydroxyl group is attached not to the secondary carbon, but to the primary carbon. This means that this is going to be in equilibrium with the ketone, but once it picks up the hydrogen here, it will make the aldehyde. So basically, hydration with mercury will give us ketones, hydroboration oxidation. Either will give you an aldehyde, or at the very least, substitution on the least hindered carbon of the alkyne. Any questions? See how much you remember from 234? We just covered Friedel-Crafts acylation. This is a nice simple way to make carbonyl compounds, arrowcarbonyl. We know that an acid halide, or an acid anhydride actually, in the presence of a Lewis acid like aluminum chloride, will generate an acylium ion like this. Acylium ions do have a lifetime in solution. They're fairly stable, but they're very, very, very electrophilic. Positive charge here. This will react with benzene ring. We do our addition step, lose a proton, regain aromaticity, and we're back to our aryl ketone. Remember, we can put virtually anything out here, so we can make all sorts of substituted things here. The carbonyl here is always adjacent to the ring. Any questions? In chapter 17, we met a very mild oxidizing agent, pyridinium chlorochromate, abbreviated PCC, usually in dichloromethane. This is what it is. This is the pyridinium ion. This is the chlorochromate. Chlorochromate is the one that actually does the oxidation. The neat thing about this is that it's a very effective oxidant, and it will stop at the aldehyde stage. Aldehydes are typically difficult to make because they oxidize so easily to the carboxylic acid. Here with pyridinium chlorochromate, we can stop at the aldehyde stage. This also works for secondary alcohols. Pyridinium chlorochromate, or just chromate and acid, will generate the ketone starting with a secondary alcohol. Any questions? If you tried to do something that would generate an aldehyde using this, it would immediately oxidize to the acid. So PCC is the only way we can stop this at the aldehyde stage. Again, if we had a primary alcohol and we tried this, we would go straight to the carboxylic acid. Now, when we get to carboxylic acids in the next chapter, this will be a fine reaction, but right now it's not giving you the carbonyls that you want. Any questions? We also looked at one very, very specific and very nice mild oxidant, manganese dioxide in something like pentane specifically and only will oxidize an allylic alcohol to the aldehyde. Remember, allylic means that the OH is attached to the carbon adjacent to a double bond. It must be an allylic alcohol, but if it is, very nice way to do it and stop at the aldehyde stage. All right, now we've covered all of these reactions, either in chapter 17 or way back in 234. Let's go ahead and just do a quick set. Go ahead and jot down the products of these oxidation reactions. Primary alcohol, PCC and dichloromethane. We know that this is mild. It will stop at the aldehyde stage. Here we have CrO3, formic acid, and sulfuric acid. This is going to oxidize our secondary alcohol here, and it will stop at the ketone stage. We will see in just a bit that this is referred to as a conjugated ketone. Conjugated with a double bond. If you think about it, this looks, if this was a carbon, this would be a diene, wouldn't it? A diene the conjugated diene undergoes specific reactions. We'll see we can do the same sort of things with an alpha beta unsaturated carbonyl. Formic acid, again, we're going to oxidize a secondary alcohol. It will stop there at the ketone stage, and we make acetophenol. Any questions? All right, well, there are a variety of reactions of aldehydes and ketones that we've looked at. These are going to, the ones we're going to talk about now, are going to be based on the fact that carbonyl compounds are very electrophilic. They're electrophilic at the carbonyl carbon. That means that the carbonyl carbon is electron deficient. The reason it is, of course, is that we can move this electron pair up to form the oxyanion. And when we do that, we generate a carbocation. Now, this is a resonance thing, remember. That means it's never this and it's never that. It's somewhere in between. But the bottom line is that the carbonyl carbon always is slightly positive. Because of that, things that have extra electrons are going to react at this center. Now we're going to look at two classes of reactions happening at the carbonyl carbon. We're going to take an anionic nucleophile and we're going to add it to the partially positive carbon. And then a second group, we're going to take a nucleophile with a couple hydrogens attached. And we're going to add that through the nucleophile lone pair to our carbonyl carbon. Doing this guy first, the anion. Again, the nucleophile simply adds to the partially positive carbon. Now here we're going to do this in a very stepwise way. Our initial addition product, we have simply added the nucleophile to the carbonyl. When we do that, the electrons must move up to make the oxyanion. This is our initial addition intermediate. Remember, this is a very rapid equilibrium process. Nucleophile can add or miss. The electrons could then move back in. Nucleophile leaves, and we're back to where we started. So it's a rapid equilibrium. Once we have this addition intermediate, typically it will pick up a proton from something, and once it does, it forms this neutral addition intermediate. This essentially traps it as the addition product. This is rapid equilibrium, this is trapping. And here we have a hydroxyl group, and our nucleophile is attached. Now, usually this is acidic enough so that we can rip off the hydrogen, go to this, and then go back. So if this is acidic, depending on the nature of the nucleophile and how good a leaving group it is, you can actually go all the way back. The other pathway here involving a nucleophile with hydrogens. Going to start off the same way. Nucleophile is going to attack, and we're going to form a Zwitter ion. And with Zwitter ion, that's a Z-W-I-T-T-E-R, simply means that we have a positive and a negative in the same molecule. This is a very, actually a very unstable intermediate, and it will kick off this as a leaving group and go back very, very easily. So once again, this is a very rapid equilibrium process. Yeah?
When you said that the other one, it can go in the other direction, but you said it's only if it's acidic
It depends
enough?
on the nature of your nucleophile. We'll see some examples.
Okay, so you should.
If our nucleophile is a decent leaving group, you can. If it's not, it's stuck. So it has to do with the nature of the nucleophile. This guy, we could pick up a proton here, we could lose a proton from here. If we lose the element of water, that is H2O, we form a double bond now between our carbon and our nucleophile. We kick out the elements of water. If this is a nitrogen, if our nucleophile is a nitrogen, this is going to be referred to as an imine, I-M-I-N-E. It is reactive just like a carbonyl is, actually. We protonate this. It can be very electrophilic on the carbon, and we're going to do some reactions of imines later on. All right, so this is an overview. Let's start off with an example of our addition of an anionic nucleophile. This is cyanide anion. This is acetone. Again, acetone, the carbonyl carbon is partially positive. We have extra electrons here. It's a good nucleophile. Cyanide will attack, and we will form an addition intermediate that looks like this. Initially, we get the anion, pick up a proton, and we get this guy. This is called a cyanohydrin. We have a cyanide, have an OH attached to the same carbon. If we did this reaction with benzaldehyde, once again, the cyanide will attack, electrons will go up, pick up a proton, and when we do that, we would form this addition product. It's a cyanohydrin. It's actually a naturally occurring product. This is bandolinitrile, it's called. It's in the oil of bitter almonds. Now, if you have almond extract or something like that, and you smell it, it has a very distinctive smell. It smells like benzaldehyde, which smells like cherries, but remember, this is an equilibrium. So the fact that you're smelling benzaldehyde also means that it has released HCN, which is bad. It's poisonous, isn't it? If you drink too much almond extract, you can literally kill yourself. Too much cyanide. Now, there's a naturally occurring product that's in peach pits. It's also a cyanhydrin. How do you say this? Amygdalin, that's it. This is amygdalin. These are carbohydrates. This is the sugar. This is the glucoside. And here we have cyanide coming down, hydrogen here, stereospecific. We have simply taken the OH, and instead of an OH, we have substituted the disaccharide. This occurs in peach pits. Well, this was suggested to be a chemotherapy agent, and it has also been described as one of the biggest chemotherapy farces that science has ever pulled off. Even some very good scientists involved. Nonetheless, this is the origin of the concept of Laetrile. Laetrile doesn't work either. Laetrile, you simply have one sugar instead of two. The problem with this stuff is that just like the oil of bitter almonds, if we take this stuff and we eat it or drink it or whatever else, as it hits our gut, there are enzymes called beta-glucosidase. Beta-glucosidase, this is a beta-glucose linkage, that's what that means, will cleave this linkage. And when it does, it forms the disaccharide and benzaldehyde cyanhydrin, which we already know is in equilibrium with cyanide. So the real problem with this is that as soon as it hits your gut, it releases a whole bunch of cyanide, and you can, again, literally poison yourself. The notion of it as a chemotherapy agent, there are tumors that have very high concentrations of the enzyme beta-galactosidase. Okay? Beta-galactosidase, again, will cleave this bond, except this must be a galactose, not a glucose. Whoever thought this up either didn't care or didn't know that there's a difference. And a beta-glucoside is not cleaved by a galactosidase. So even if this did get up to a tumor cell, it has the wrong enzyme. The idea was that this would release cyanide inside of the tumor cell and kill it. But again, the sugar is wrong. Another nucleophile that we can add, now this isn't anionic, but it's the same sort of mechanism, and that's water. If we take water and we add it to a carbonyl, what happens is we form this very unstable zwitterion intermediate. Again, the water adds, when I say unstable, that means that it's going to go back really, really fast. Okay? Because water is a very good leaving group here. Carbonyl reforms, kicks out water. But if this thing manages to live long enough to lose a proton, we would form this intermediate. Now we have a lousy leaving group. Hydroxide is a lousy leaving group. Once we get to this point, All we have to do is stick a proton on here, and we make what's known as a 1,1 diol. 1,1 because both OHs are attached to the same carbon. This is also called a carbonyl hydrate. Carbonyl plus water, H2O, we've added H2O. This is all a very rapid equilibrium. Now the amount of carbonyl hydrate that you have is going to depend upon the inherent reactivity of the carbonyl compound. Aldehydes are more reactive than ketones. Hydrogen is little. Usually the alkyl group attached here is much bigger. Therefore, all reactions tend to be slower with ketones. For the hydration, if you look at acetone at equilibrium in water, we have about 0.1% hydrate. If we have formaldehyde, the ultimate aldehyde, we have 99.9% hydrate at equilibrium. So again, it's a simple function of the reactivity of the carbonyl, and aldehydes are always much more reactive than ketones. Formaldehyde is an interesting compound. You can actually take formaldehyde hydrate, remember how we just added water? Well, we can add one of these hydroxyl groups to another formaldehyde. When we do that, we form this guy. We can do the whole process again and form this, the cyclic triether. This is what it looks like actually. There's got 3 oxygens in there and our CH2s. This is all in equilibrium again. So if you have formaldehyde in water, you actually have a lot of this stuff. You may have used what's known as paraformaldehyde in a biology lab. Paraformaldehyde is basically a high molecular weight polymer based on this stuff just reacting with formaldehyde to make this long chain of polyethers. Once again, it's all at equilibrium, so if you have a long polymer, we can still break it down to make or serve as a source of formaldehyde. Any questions? Now, a very important reaction that is based upon this same sort of chemistry is the formation of diethers, 1,1 diethers. If you do this with a ketone, a compound like this, we call it a ketal. This is an equilibrium. So if you have, say, acetone in the presence of ethanol, you'll form a little bit of this at equilibrium, acid catalyzed. If you keep track, as we add 2 of these things, we lose the elements of water. So if you do this under conditions where we can remove the water, then we can make the ketal as a stable addition product. If we do this with an aldehyde, we form, again, a 1,1 diether and call that an acetal. Ketals and acetals are important in carbonyl chemistry because it's a really nice way to protect the carbonyl. If you want to use a carbonyl compound in a reaction of some sort, but whatever reagent you're using would react with the carbonyl, what you do is convert it to a ketal or acetal first, do your chemistry, dump it in acid and water, and convert it back. Very nice, very simple way to protect a carbonyl. the mechanism for the whole thing. It's going to be the same sort of mechanism we've talked about. We're going to take our carbonyl in the presence of acid, start off by protonating it. Now that makes this really, really positive down here, doesn't it? It really enhances this as an electrophile. Our oxygen from the alcohol will attack, form this intermediate. Again, this is fairly unstable until we lose a proton here, and we get this thing. These things, if you have an ether on one side and an OH on the other, that's called a hemiacetal, half of an acetal or hemiketal. This guy can react with acid again. We're going to protonate here. Now we have our water as a superleader group. This is going to kick it out. Get our carboxonium ion here, or oxocarbonium ion. This is very electrophilic, very similar to this. This adds another alcohol. And finally we get this thing, lose a proton, and you're at the ketal or acetal stage. If you're counting, again, we've lost the elements of water. If we can remove the water, we drive the reaction this way. If we add acid and water back, we drive the equilibrium this way. Any questions? We've seen a reaction very similar to this. This simply says what I just said. If we add aqueous acid, we go back. If we remove the water, we go forward. Reaction that we saw not too long ago in the chapter on alcohols, we said that we could take this dithiol and form this cyclic thioketal. Now again, we can do this with oxygens, and we make a cyclic thing with two oxygens. But the neat thing about this one, that we said in chapter 17, is that once we're at this stage, we can reduce this off. That we can reduce the dithioketal. Radionickel. Radionickel is simply it's just finely divided nickel containing adsorbed hydrogen. It's a really neat reagent to use because you don't need a hydrogen source. You just take uranium nickel, spoon it in, and your reaction goes. Very simple. And we convert the carbonyl into a CH2. So it's a nice way to get rid of a carbonyl. Any questions?
So basically, in summary, if you add water to ketone and carbonyl, you're creating a ketone or acetal, and
Yep, you'll take it, push it all the way back. Has to have a little bit of acid in there to catalyze it. So acid catalyzed forward. If you remove the water, add water back, it goes all the way back. Now, this is glucose. Glucose is a sugar. You can draw glucose as an open chain like this, but if you notice this open chain, the way I've got it wrapped around here, the hydroxyl group is 6 carbons away from this aldehyde carbonyl. Now remember what we just said about alcohols reacting with aldehydes. They do it well. And the fact that this is 6 centers away, we have what's known as an entropy-driven reaction. Things that form 5- and 6-membered rings are favored. Therefore, this hydroxyl group will attack the carbonyl. When it does, this picks up a hydrogen out here and forms a hemiacetal. This is the cyclic form of glucose. Glucose exists largely as a cyclic form in the hemiacetal. This is an equilibrium, of course, but most of it is present as the cyclic hemiacetal. Now, if you think about it, this hydroxyl group could attack the way I've shown, that is coming in on this side. We pick up the hydrogen here, or it could come in and attack the bottom. If it attacked through the bottom, we would get the opposite stereochemistry here. Glucose exists as two stereoisomers. They differ in the absolute configuration here at this. This is called the anomeric carbon. Anomeric, A-N-O-M-E-R-I-C. There it is, anomeric carbon. This is an enantiotopic, axial and equatorial. Again, it's called the anomeric carbon. These have trivial names. You may have seen glucose described as beta-D-glucose. Beta simply refers to the stereochemistry here. The enantiomer at this carbon is alpha-D-glucose. D refers to the stereochemistry at this carbon. All sugars are basically D stereochemistry here. D is S. Old-fashioned version of S. So beta-D-glucose and alpha-D-glucose. Simple hemiacetals. All right, go ahead and run through a set of these simple carbonyl reactions, and we'll talk about them. In our first one here, we have benzaldehyde. We are in methanol in the presence of an acid. That means we're going to form an acetal, aren't we? We're going to have a 1,1 diether, 2 methoxys attached at this carbon. In our next one, we have ethylene glycol. Now, ethylene glycol is a 1,2-diol, this stuff. What happens is, one oxygen will attack to form the hemiacetal, and then we have the entropy-driven 5-member ring closure. Entropy-driven reactions are roughly 1,000,000 times faster or more specific than things that are not entropy-driven, referred to as the Cersei effect, actually. But, so one attacks, then the other, and we form the cyclic ketal. Whoops. Get out of there. Cyclic ketal looks like something from a video game. Ethylene glycol is widely used as a protecting group. So if you had this, you wanted to do some chemistry that you couldn't do with carbonyl present, you make the ketal, then just dump in acid and water, and you're back. Yeah.
So, how do you know that it's entropy driven? Like, how would you know for a different?
Well, because I told you so.
Okay, so there's no other indication.
Yeah, inorganic chemistry, if you can close to form a 5- or 6-membered ring, that's a good thing. So always remember that, always look for that. Entropy driven. Here we have a cyclopentanol, but the chemistry is going to be the same. It's just going to be a weird looking compound with 2 cyclopentyl ethers. Any questions? All right, let's go ahead and look at the second group. These are going to be nucleophiles that have hydrogens attached that we can lose. What we're going to do in these is we're going to lose the elements of water, typically to make a carbon-nitrogen double bond. Now the mechanism of the reaction is pretty much the same. Here we're going to have an amine as our neutral nucleophile. Again, this has a lone pair of electrons. And because of that, this is going to be a nucleophile towards a carbonyl. Initially, we're going to form this zwitterion. Very unstable. Very unstable. We can move the electrons back, and we kick out a neutral amine. Very good leaving group. In order for this to survive, we have to somehow trap this intermediate. If we take and we lose a proton here, now we've lost our good leaving group. This would leave as an amine anion, not a neutral amine, and that's a very bad leaving group. Strong bases, bad leaving group. If we took this guy and we put a proton up top, oh, here's the other pathway down here. We could also trap this intermediate by putting a proton on here. We still have a good leaving group, but we don't have electrons to push with anymore. Finally, both of these, we can protonate here, lose a proton here, to get our neutral addition intermediate. Now, all the steps in this reaction might seem, oh, I don't know, irrelevant, but frankly, it was the understanding of this intermediate and these particular trapping steps that really led to a detailed understanding of these types of reactions. And these reactions are important because once you make this neutral intermediate can undergo an acid-catalyzed dehydration. So we put a proton up top, we're going to push it off with this electron pair, and we form a carbon-nitrogen double bond. Once again, this is an imine, I-M-I-N-E. This is the iminium cation, simply because it's protonated. Obviously, we can lose this at equilibrium. The reason that this is so important, we've all heard of B vitamins, right? B6, for example. B6 is pyridoxal phosphate. Pyridoxal phosphate is used in modifying amino acids, and the mechanism for that reaction involves the formation of an intermediate imine. That's how it transfers the amino acid portion from, say, a non-essential to an essential amino acid, etc. Very important in biochemistry. All right. Let's go ahead and look at some alpha effect amine nucleophiles. Now, we've done this in lab. Remember, we used hydroxylamine and I think benzophenone to make an oxime. Once again, this is hydroxylamine, simply ammonia where we've taken one hydrogen off and put an OH in its place. Like I said, these are called alpha effect nucleophiles. What that means is, this is our nucleophile right here, the nitrogen. But right next door, the alpha position, we have something with a lone pair of electrons. That makes it a really super nucleophile. What's going to happen is the nitrogen will attack, will form our intermediates. We'll then lose water. We replace the carbonyl, we're going to lose H2O, and we're going to form the oxy. Once again, a carbon-nitrogen double bond.
So you said it's an alpha effect nucleophile, which adjacent to it would be something containing a lot of electrons?
Right.
Okay.
This is semicarbazide. It's also alpha effect nucleophile. Here we have a nitrogen with a lone pair of electrons. This is our nucleophilic nitrogen. This half of the molecule, the NH, this stuff right here, that's actually urea. Carbonyl with an NH2 on both sides. Once again, the nucleophilic nitrogen is going to be this guy. It's the alpha effect. It's going to attack. We're going to lose water. For these types of reactions, all you really have to remember is that the oxygen goes, we attach this nitrogen in its place, and everything else just goes along for the ride. This is what the product looks like, semicarbazide. This is referred to as a semicarbazone. Simply replace the oxygen with our nitrogen, and all the rest goes along. Now in lab, I wish we did qualitative organic analysis, because it's a very good way to learn simple functional group reactions. We don't do that. But if you have a compound that you think is a ketone or aldehyde, the way you test for it is what's known as 2,4-DAP, 2,4-dinitrophenyl hydrazine. This is also an alpha effect nucleophile. This is our nucleophilic nitrogen next to another nitrogen with a lone pair. So it's a very good nucleophile. The nice thing about 2,4-DAP reagent is that it's soluble in water, in acid actually. But the hydrazone that you make, the product, is not. This is also a very bright yellow compound due to the nitro groups. So what happens is when you just take a solution in, say, water or alcohol, a little bit of alcohol, containing a carbonyl, and you add 2,4-DMP reagent, you get very rapid formation of this stuff, which is the 2,4-dinitrophenyl hydrazone. These are almost always insoluble in water. The reaction occurs instantly, and you get this wonderful yellow precipitate falling out. So if you have an unknown that you think is a carbonyl, aldehyde, or ketone, dump it in, get a bright yellow precipitate, that's your stuff. Collect your precipitate, recrystallize it, do a melting point, you can actually identify what the carbonyl compound was. Any questions? Well, these are all alpha effect nucleophiles. Let's go ahead and do these with some standard amine nucleophiles. Go ahead and write the products for these reactions. Chemistry is going to be the same. The nitrogen is our nucleophile. We're going to form a carbon-nitrogen double bond. Ethylamine, nitrogen attacks. We would form the imine, I-M-I-N-E, again, carbon-nitrogen double bond. Now this is a nitrogen, so it has a lone pair. You can protonate it as the iminium cation. So you could write either one as a product. This is aminobenzene, better known as aniline. Chemistry is the same, however. Nitrogen attacks, we lose water, form a carbon-nitrogen double bond. Once again, we can protonate this and make it positive. Our last one is a secondary amine, isn't it? Chemistry is going to be exactly the same. Nitrogen is going to attack, going to lose water, but our product here is going to be this. We have a secondary amine, so there's no hydrogen to lose, is there? This is stuck as being a cation. So typically, if we have a simple primary amine or arylamine, we will wind up with a nice neutral imine, no problem. However, if we have a secondary amine, we get the iminium cation. Now, the reason the iminium cation is particularly interesting is because it's so very unstable. If you take a secondary amine, react it with a carbonyl, once again we form this intermediate. But this is unstable because we can form a neutral compound from it. To do the neutral compound, we're going to pull a proton off that's adjacent to our double bond. Our electron pair will move up to our nitrogen, now it's neutral, and we get this stuff. This is an ene amine. Ene refers to the fact we have a double bond, and it's attached to the same carbon as the amine. So, bottom line, if you do a secondary amine, treat it with a little bit of base, it will go quantitatively down to the enamine. Now the enamine is going to be important to us because we can use this as a nucleophile. Just like I said with an enol, remember? I said in enol we have electron density. Use that as a nucleophile. Enamine is even better. If we take an enamine, we can take and move this electron pair back in and make a resonance form that looks like this, with a nice negative carbon sticking out here. Later on, we will, maybe the next, not the next chapter, but the one after that, we will use this as a nucleophile towards other carbonyls. Any questions? Enamines, lots of electron density here, good nucleophiles. All right. Another alpha effect nucleophile reacts just like hydroxylamine. It's called hydrazine. Hydrazine is somewhat infamous. It's used as rocket fuel, etc. Again, it's just an alpha effect nucleophile. We have a nucleophilic nitrogen adjacent to something with an unshared pair. Good nucleophile, this can add, and it can form this imine. Not surprising, you all could have drawn that structure. But the neat thing about this hydrazone is that we can treat this thing with base. If we do, we can remove one of these hydrogens, and we can do what's called a reductive elimination. So after we make our hydrazone, if we go and we dump in KOH, what happens is a two-step reaction. This is known as the Wolff-Kishner reduction. Step one, the base pulls off the hydrogen, pick up a hydrogen on this carbon to form this intermediate. Now remember, nitrogen itself, N2, is a very, very stable molecule. Most explosives are based on the fact that things with nitrogens attached really want to be nitrogen gas. Okay? And when they do, it generates energy and, of course, nitrogen gas. Well, this thing really wants to be nitrogen gas. In the presence of our strong base, this can undergo another elimination. We form this really unstable alkyl carbanion and nitrogen. That's the driving force. This will immediately pick up a proton, and by gosh, we made an alkane.
What kind of reduction did you say this was?
It's a reductive elimination. We're eliminating nitrogen, and we are converting carbonyl into a CH2.
Because that like little snippet that you had in the beginning isn't in the.
Yeah. Reductive elimination. Now, we just talked about thioketals being reduced by nickel, Randy nickel. This is another way, the Wolff-Kishner reduction again. You take this, treat it with base, carbonyl down to a CH2. If you recall, we also know another way to do this. This is the Clemenson reduction. Clemenson reduction, we said, was an accident. Zinc mercury amalgam, stirring it too roughly with a broke thermometer, etc., converts an aryl ketone, in this case, to a CH2. Can also do it with virtually any other ketone, again, to a CH2. Aryl ketones, we know we can also simply reduce off with hydrogen. Let's go ahead and just do these two Wolff-Kishner problems. Our initial product is going to be the hydrazone in the presence of the strong base. Hydrazone is going to lose nitrogen. Our carbonyl is simply going to become a CH2. And the one on the bottom, again, we're going to make the hydrazone here. Strong base, we're going to eliminate nitrogen gas and just convert that to a CH2. One hydrogen attached makes it a methyl group. Now where this is really useful, remember it's easy to stick an acyl group like this onto a benzene ring, isn't it? We just do that with the Friedel-Crafts. But sometimes after you get it on, you want the carbonyl gone. And this is a nice simple way to get rid of the carbonyl. If you stop and think, we know several ways to do this. Again, if it's an aryl ketone, we can reduce it off just with hydrogen. Virtually any ketone, we can use the Wolff-Tishner reduction, ketone or aldehyde. We talked about this a little bit ago. This makes our thioacetal. Again, in the presence of raney nickel, that's reduced off. And this is the Clemmensen reduction. Take any carbonyl, doesn't have to be aryl, Clemmensen reduction to the CH2. These types of reactions, again, are important because synthetically, sometimes you want to introduce a carbonyl, do some chemistry, and then get rid of it. So these are those very simple ways to do that. All right, let's look at one more addition reaction, actually a couple more, that we've already talked about. Back in chapter 17, we talked about the reduction of carbonyls with lithium aluminum hydride. Very simple reaction. The hydride here, the aluminum hydride, this hydrogen with its pair of electrons is our nucleophile. Again, this is our electrophilic carbon. Form our addition intermediate, pick up a proton here, and we would form the neutral addition intermediate. Because this is a lousy leaving group, H minus, very strong base, lousy leaving group, this is not equilibrium, it's irreversible. Simple addition of an anionic nucleophile to a carbonyl. Sodium borohydride, we know we can do the same thing. Remember we saw the cute little film with burning lithal. Lithal is very dangerous, has to be done in ether. It burns spontaneously in moist air. Not something you want to play with, but it's much more specific than borohydride. If we didn't have the double bond, borohydride would be the reagent of choice. But in a case like this, we would get reduction here, and we'd also get reduction as a double bond. Lithal is much more specific. We get virtually only the carbonyl reaction, but it's dangerous itself. All right, let's do a quick set here. Go ahead and draw the reduction products. These are all borohydride. Again, you could do this with lithal as well. All in the world you do here is you take your carbonyl compound and convert it to an alcohol. Very simple, specific reaction. Here we make our secondary alcohol. This is an aldehyde, so we're going to make a primary alcohol. This is acetophenone, so again we will make a secondary alcohol. Very simple, very specific reaction. Don't have to worry about reducing the ring. Remember, the ring reduces very, very slowly. Any questions? All right, also back in chapter 17, we covered the ultimate carbonyl addition reaction, and that's our Grignard. We had this on the exam, everybody got it right. all the world that happens here is our anionic carbon adds to the electrophilic carbonyl. We wind up with an addition intermediate. It's stable, again, because if we went backwards, this would be an R minus. Very strong base, lousy leaving group. So we make this as our addition intermediate, simply protonate it, and we make the alcohol. Go ahead and do a simple set of Grignards. In the presence of magnesium and ether, this will be converted to methyl magnesium bromide. Methyl group will be our anionic nucleophile. It will simply add to the carbonyl here. When it does, we will make the secondary alcohol. Aldehyde, secondary alcohol. Grignard also works nicely with aryl halides. This will make phenyl magnesium bromide. The phenyl anion is our nucleophile. Again, it's an aldehyde, so we will make the secondary alcohol. And finally, if we're dealing with a ketone, ketones, this would react with cyclohexyl magnesium bromide to give us the tertiary alcohol. Now remember when we talked about doing Grignard reactions, we said that there were typically two pathways you could follow. Now we did this at our last exam. We're going to do this again because it's an interesting concept question. If we wanted to make this secondary alcohol, we could make this by two pathways. What I'd like you to do quickly is to draw the two carbonyl compounds and the two Grignard reagents. Now, the way we said to do this was to say to ourselves, this used to be the carbonyl. Carbonyl could belong to this half of the molecule or this half. So, split somewhere on either side. If this was the bond we made to make our alcohol, then that means that this side here had to be the aldehyde, and this side here had to be the Grignard. Our Grignard had two carbons, so it's ethyl magnesium bromide. Our carbonyl compound has 1, 2, 3, 4, so it's butan-al. Now if we split on the other side, that means that this used to be the aldehyde, and this part here was our Grignard. Our Grignard had 1, 2, 3 carbons, so it was propyl magnesium bromide. Our aldehyde had 1, 2, 3 carbons. It's an aldehyde, we can even name it now. This is propan-al. Now make sure you understand the logic in doing this type of a synthesis, because we're going to see something like this in just a moment with a new reaction called the Wittig reaction with a W. Before we do that though, let's just remind ourselves that Grignards are great, except we can't do them with anything that is acidic, and that's because Grignards are really strong bases. They just yank a hydrogen off. Grignard goes to the alkane. Can't do it with anything acidic. Again, anything that can do an addition of a strong nucleophile can't be in there either. Now our last reaction out of review time. Again, back in chapter 17, we talked about using an alkyl lithium as a nucleophile. Made simply from lithium metal, alkyl halide of some sort, very versatile. Once you make it, this carbanion can act just like a Grignard, and we can do a reaction. For example, if we have R lithium, or R is virtually anything, the R minus attacks our addition intermediate. It's stable because we can't kick out R minus, protonate this, and we get our alcohol. For example, if we had this ethynyl, this vinyl lithium, reacting with benzaldehyde, what would we get? Our nucleophilic carbon here is this guy. Looks like it's really busy, but that's it. This is the carbanion. We're going to form a bond between this and the carbonyl carbon. When we do that, this is going to be the OH. We have a bond now from here to here, and our product would look like this. This is the bond we just made. Again, the rest of this is from benzaldehyde. All right, again, we've done lots and lots of review here. The good part about that is that you already know all this stuff, right? This is a new reaction. It's called the Wittig reaction. Wittig, a German chemist. W is pronounced like a V. In the Wittig reaction, we're going to take a carbonyl compound, an aldehyde or ketone, and we're going to react it with what's known as a phosphorus ylide. Phosphorus ylide is a Wittig ion, but in order to be an ylide, the anion and the cation must be adjacent to each other. This is going to react as if it was a simple Cr2 group. All that happens is that this guy is donated, as is, and shows up where the carbonyl oxygen used to be. So think about the amine forming reactions, right? We replace the carbonyl oxygen with a nitrogen, didn't we? Here we're converting the carbonyl into an alkene. Now the neat thing about this is, gosh, we know lots of alkene chemistry, don't we? So once you do that, we can do lots of chemistry on the thing that we make. It works well to make mono and di and tri-substituted, so 3 things, but not 4. The mechanism. To make our illid, we take triphenylphosphine. So this is a phosphorus with 3 phenyl groups attached. Phosphorus, just like nitrogen, has a lone pair, and it's a nucleophile. It's simply going to react with the alkyl halide, and we're going to form this addition intermediate. It's a phosphonium salt, just like ammonium salt. 4 things on phosphorus. Remember, phosphorus is right here underneath nitrogen. Ammonium, phosphorus. So our phosphonium salt, in order to do the reaction, we have to make the illid. We make the illid by treating this with a strong base. Strong base. This is an alkyl lithium. We just used that, right? You can get bottles of stuff like butyl lithium here. Nice, stable, very, very, very strong base. This will pull this hydrogen off. When it does, it generates the illid. So the way you see these things represented sometimes will be the simple alkyl halide plus triphenylphosphine followed by base. You're supposed to remember that this makes the illid. Take the halogen off. This is a nucleophilic chunk. The reaction. Our nucleophile is going to add to the carbonyl carbon. When it does, we form this simple addition intermediate. Okay, we've done this over and over again. However, this oxygen is right next to this phosphorus. And this can undergo a cyclic rearrangement. When it does, we form this intermediate here, where now we have this bond formed. But then this decomposes like that to give us phosphine oxide and the alkene. Now we're probably not going to draw the mechanism of this on an exam, but it's nice to know anyway. We have this cyclic intermediate, decomposes. Bottom line to remember, nucleophilic carbon, replace the oxygen, and make an alkene. Any questions? All right, let's do a synthesis. We're going to start here with cyclohexene, and we're going to make methylidine cyclohexane. Now, what you want to do when you do any synthesis, remember, is to start with your final product, take a peek at what you're starting with, and then just ask questions about this. What is it? How do I know to make it? Obviously, the cyclohexane ring is going to come from our starting material. We must add a CH2. We're going to be making an alkene. When we're adding a carbon or 2 or a chain or whatever, and making an alkene, you should always think Wittig reaction. So very quickly, write for me. the Wittig reagent we would need, and the carbonyl compound that we would need to make this. Now, I hope you've realized that there are two ways we can do it. Because when we make the double bond in a Wittig reaction, the carbonyl could have been up top, or it could have been on the bottom. Could be either one. But let's go ahead and do the simple thing, and that is clip off our CH2 and simply use the methylidine illy. That means our carbonyl was on the cyclohexane, and all we've done here is add our CH2 and make the double bond. Now we have a totally new synthesis problem. We have to somehow make cyclohexanone from cyclohexene. So we know all this. We know we could make this if we had an alcohol and we oxidized it. That's how we could make this ketone. So, go ahead and write for me the structure of the alcohol and a typical oxidation reagent. The alcohol simply must be cyclohexanol, right? Secondary alcohol. There's lots of ways we can oxidize a secondary alcohol. PCC and dichloromethane, always a good choice. Now, we have yet a third synthesis problem. We have to convert cyclohexene into cyclohexanol. My gosh, chapter 6, isn't it? We know a couple nice simple ways to make alcohol from an alkane. Hydration, we can do simple acid catalyzed hydration. We know that that's a little bit brutal. We could also do mercury catalyzed hydration. We could also use hydroboration, oxidation. Here I've done mercury 2 acetate followed by borohydride to get the alcohol. By the time we finish this course, this simple 3-step synthesis will be routine. Chapter 6, Chapter 17, Chapter 8 of 19. Any questions? All right, remember I said we could do this thing 2 ways, right? Let's explore that with this synthesis. Our carbonyl could have been up top, or it could have been on the cyclohexane. Go ahead and look at this, and let's deal with the top one first. If this was our Wittig reagent, what would it be? And draw the structure of the ketone. So our top group here comes from the Wittig reagent. The bottom is our ketone.
Like you on the Wittig reaction is just that, the one with the P in it, right? That's our only mechanism for that, or solution, or?
Probably don't need to know the mechanism, no. Just know how to use it. And this is how to use it. This stuff, the CH2, this CH, this was the anion of the ylide, right? So this carbon was an anion attached to our phosphorus, our triphenyl phosphorus. This carbon down here was a carbonyl, cyclohexanone. I guess I did this backwards. Oops. Sorry. So this was the other half. Here we use this as our Wittig, and here as our carbonyl. Sorry, I got those reversed. Now, the one that it's also going to be wrong, I'm sure, is the other option. Here, the cyclohexane is our Wittig. This is the carbonyl. Let's go ahead and write the other product, again, where this is the carbonyl, that's the Wittig. And it should look like that. So bottom line, you take each of the carbons, they could either one be the carbonyl, again, split it. This half could be the Wittig, that's there, or this half could be the Wittig, that's there. In a while, we will do a whole bunch of reactions to review all of this, and we'll do these types of Wittig reactions again. So we'll come back to this in just a minute. There is, however, one more new reaction that we have to do. Now, I'm going to go here to chapter 12, I think. In chapter 12, we talked about dienes undergoing addition reactions. We said that we could do 1,2 and 1,4 addition because we have these resonance forms. 1,2 addition, we add this carbocation. 1,4 we would add here. That's a simple diene, conjugated diene. Well, like I said earlier, if instead of having a carbon here, we had an oxygen, we would have a conjugated ketone or aldehyde. Again, this gives us our 1,4 mechanism, simply adding to this carbon. All right, let's go ahead and convert this to an oxygen now. I will call this an alpha-beta unsaturated ketone or aldehyde. Alpha always refers to the carbon adjacent. Beta is one removed. In chapter 21, we will do lots of chemistry on alpha-beta unsaturated carbonyl compounds. So this is just a nomenclature. All right, think about the alpha-beta unsaturated carbonyl. If we have a nucleophile, we can do a 1,2 addition here, can't we? That's what we've been doing, simply adding to the carbonyl carbon. But this thing exists as these resonance forms as well. That is, we have positive charge here, which is where we've been adding up till now, and we have positive charge on the beta carbon. Now, addition to the carbonyl, a 1,2 addition, if you will, we've been saying that is rapid and it's at equilibrium, isn't it? go and come off, go and come off. However, the 1,4 addition is not at equilibrium. If our nucleophile attacks here, we wind up with a stable product where again our nucleophile is now in the beta position. Again, it's analogous to 1,4 addition. So, if you have an alpha-beta unsaturated carbonyl compound, you can add here rapidly at equilibrium, or you can add to the beta carbon irreversibly. So let's look at some examples. If we take a nitrogen nucleophile, we've done this. We know we can add to the carbonyl and make an imine, right? But that's reversible, isn't it? It goes on and goes off. This nitrogen can also add to the beta carbon. And when it does, this nitrogen is bonded out here. And that's our product. This is referred to as conjugate addition. It's a conjugated system, conjugate addition. Addition to the beta carbon. Again, methylamine can add at equilibrium here. Or, because this is conjugated, it can add here. And our product is this addition intermediate. One-two addition, that is to the carbonyl, is rapid and reversible. But if it's a conjugated system, we can also add to the beta carbon to make beta or conjugate addition, which is essentially irreversible. Remember cyanide, we added HCN to carbonyls, formed cyanohydrins. Rapid addition to the carbonyl, right? Cyanide can also add to the beta carbon. Now you can do this with HCN. This diethyl aluminum nitrile is a much better reagent for that, actually. Diethyl aluminum nitrile, again, is a glorified CN minus. This is simply going to attack at the beta position. When it does, we've made our conjugate addition product. Same thing here. Cyanide is going to attack at the beta carbon. When it does, this is our final product. One last reagent. This is a dialkyl copper lithium. Now we actually talked about these way back in chapter 1 or 2 or something like that. These can react with an alkyl halide to form an alkane. We didn't really care about it at the time. We've probably forgotten about it. The nice thing about a dialkyl copper lithium, however, is that this can react very nicely and donate one of these alkyl groups to the beta carbon of an alpha-beta unsaturated carbonyl. So, methyl group attacks. We have now extended our chain here by 1 carbon. This is no longer a double bond. and we've made 1, 2, 3, 4 butanal. We can also make dialkyl copper lithiums with vinyl groups, aryl groups, etc. Again, we talked about this in chapter 2. Same chemistry though. This as an anion is going to add to the beta position. So here's the carbon we added just in case you're keeping score. Here we're going to add this. Going to wind up with a double bond attached here, and it would look like that. Any questions? So we have two really new reactions. We have the Wittig reaction, and we have conjugate addition. Let's go ahead and just look at a bunch of problems. First of all, just provide reagents that I would need to do these transformations.
There's only 3 reagents, right?
No, this goes all the way back to chapter 6. Organic, you can never forget anything. Not even chapter 2.
The exam should have matching.
All right, what have we done here? We have added a methyl group to our beta carbon, haven't we? We know we can do this with a dialkyl copper lithium. And the alkyl group is simply dimethyl copper lithium. Our next reaction, we're making an oxime, aren't we? This is the equivalent of a 1,2 addition. That is, we're adding to the carbonyl, not to the beta carbon. All we need to do this, remember we're going to lose water. So this is going to be NH2OH, that is hydroxylamine. We even did this in lab.
For the first one, I thought that you had said before that you could use the Wittig if you're adding a carbon.
Well, if we did a Wittig, we would be replacing the carbonyl.
Oh, okay. So it'd be the wrong carbon.
Right. Okay, our last one. On this page, we go on and on. We're dumping our carbonyl, aren't we? My gosh, we know 4 ways to do that. Reduce the dithioketal, Wolff-Kishner reduction, Clemmensen reduction. Actually, only those 3 would work. Simple way to do this, either Clemmensen, thioketal, or Wolff-Kishner. You get to choose. I chose Wolff-Kishner. Make the hydrazone, treat it with base. Let's do 3 more. Now, once again, we have added something to the beta carbon, haven't we? This is going to be a conjugate addition. We can make diaryl copper lithium, just like we can dialkyl. Our diaryl copper lithium reagent, simply 2 benzene rings, copper lithium, and it would look like that. All right, what's this spider? It's an enamine, isn't it? Enamine, double bond and an amine. How do we make enamines? We simply make an imine with a secondary amine, treat it with base, and it forms a neutral enamine.
So that nitrogen has to go here.
Nitrogen must be secondary amine. Our reaction conditions, if we simply take diethylamine, this can actually function as its own base, pull off the hydrogen, and make the enamine. Our next one is what? It's a ketal. We know how to make ketals. Just need an alcohol in the presence of acid. The alcohol we need is what's derived from the ethers here. That's simply methanol. Methanol in the presence of acid. One more of these. Taking benzaldehyde and we're making these guys. I guess 2 more of these.
Maybe 3.
All right, what we've done here, we've added a methyl group, haven't we? And we made a secondary alcohol. How do we do that? Converting an aldehyde to a secondary alcohol, that should scream at you, Grignard reagent. The Grignard is going to be simply methyl magnesium bromide. Carbonyl, now you see it, now you don't. 4 ways to do it, right? Simple reduction, thioketal reduction, Wolff-Kishner, Clemenson, your choice. Simple catalytic hydrogenation will work fine. Remember, this only works if it's an aryl ketone or aldehyde. It has to be attached directly to the ring. What is this guy? It's an imine, isn't it? How do we make imines? Carbon-nitrogen double bond. Take a carbonyl compound and react it with an amine. What amine? Well, it used to have 2 hydrogens and a benzene ring. This is anil. And our last one, I think. Benzaldehyde to benzoic acid. How do you do that? Remember, it's actually very easy to do. If you have a bottle of benzaldehyde sitting around the lab, it's always got this white crusty stuff around the lid. That's benzoic acid because it's oxidized by the air, so easily oxidized. Any oxidizing agent will do. We can't use PCC because that's not strong enough. We have to oxidize it all the way to the carboxylic acid, so Jones reagent or something like that. This is the ketone, isn't it? Both oxygens came from the same alcohol. That's why it's cyclic. Because it's cyclic, we need a 1,2 diol. So we have OH, CH2, CH2, OH, or ethylene glycol. And finally, we have benzaldehyde, and we're making benzyl alcohol. Very simple reduction, isn't it? We know two ways to reduce it. Lithium aluminum hydride, which explodes, or borohydride, which doesn't. Let's use borohydride. Any questions? Yeah,
With the first one, is KMnO4 acceptable?
yeah, yep, that'll work.
What would it be with KMnO4?
In acid. All right, now we're going to do reactions. Here we have ethylene glycol reacting with an alpha beta unsaturated ketone in the presence of acid. We know an alcohol reacting with a carbonyl in the presence of acid will form a ketone. Go ahead and draw the structure of our ketone.
Beta carbon?
No, no. Remember, our beta additions that we talked about were dialkyl copper lithium, cyanide, and amines. Because this is a 1,2 diol, it will be cyclic. Our double bond won't be touched. It'll just look like that. Now you see, this is why you would use this in a synthesis. Because let's say we wanted to do some reaction here of our double bond. We know lots of double bond reactions. We can make the ketone, do our chemistry here. When we're done, dump in acid, and go back to a carbonyl. Our next one is a Grignard reaction, isn't it? We have an aldehyde, so we will make a secondary alcohol. This is going to be an OH, and we're adding this 1, 2, 3, 4 carbon chunk to it. Here's what we added. This is acetaldehyde. Hydroxylamine reacts with carbonyls to form what? Oxenes. Carbon-nitrogen double bond with an OH dangling off. Secondary alcohol, PCC, and dichloromethane. PCC, we remember from chapter 17, is an oxidizing agent. Pyridinium chlorochromate. It will convert the alcohol smoothly into the carbonyl. Simple borohydride reduction of a carbonyl. How simple can it be? All you do is add hydride, convert the carbonyl into an alcohol. Cyclic ketal, presence of acid. We're going to hydrolyze this. I say show all products. That means I want you to write the alcohol and the carbonyl. Carbonyl, well, this is going to be the carbonyl carbon, and the rest of this will be the alcohol. Here's our alcohol, 1,2-diol, and here's our carbonyl compound. HCN reacts with simple aldehydes and ketones to get what? Cyanohydrins. Cyanides are nucleophile. Our carbonyl is simply converted to an OH. This is the Wittig reagent, isn't it? Whenever we see the Wittig reagent, we know we're going to replace our carbonyl with this carbon. And it will be an alkene. Now I've drawn this trans because, as you can imagine, this is big. So it's going to want to stay away from the ring as much as it can. The trans would be your preferred product. Then make sure you see this. This is the chunk that we just added. The CH3CH, CH3CH, replacing our carbonyl. And our last guy here, secondary amine and an aldehyde. What's going to happen? Going to form an ammonium ion, going to lose a proton and make the amine. Alkene and an amine. Looks like it could fly. One more of these. Chapter 17, lithium aluminum hydride and an aldehyde. What do we get? We're adding H minus, that's all. Aldehyde will go with primary alcohol. Chromic acid, strong oxidant. Primary alcohol. We're not going to stop at the aldehyde, are we? We're gonna oxidize this all the way down to the carboxylic acid. It's CH2, it's this carbon. Oxidize all the way to the carboxylic acid. And here we go, chapter 6. We have an alkyne. We're going to do Markovnikov addition here, aren't we? We have a choice, secondary position or benzylic. Benzyl is going to win. We will make this aryl ketone. All right, let's do a couple of these. Wittig synthesis, 2 ways. Remember, in the Wittig, either this one or this one used to be the carbonyl. If we split this, that's the double bond we made in the Wittig reaction. So, this half right here could be a carbonyl, and this half from the Wittig, or all the way around, this could have been the carbonyl, and this the Wittig reagent. Go ahead and write your options. One set. If we keep this as our carbonyl, then this would be acetaldehyde, wouldn't it? This was a carbonyl attached to a CH3. That means that this half was the Wittig reagent. Wittig reagent had a CH. This is the isopropyl group attached to it. And it would look like this. Here's our CH, this one, and here's the isopropyl. This is the carbonyl half. If we do it the other way, carbonyl would have been this side. It's an aldehyde. Longer chain is 1, 2, 3, so it's a prop, propanal, with a methyl group in carbon 2. Our Wittig reagent, CH3, CH. Now this one is review. We're going to do Grignard. We're going to split this into 2 Grignard reactions. Want to split on both sides of the OH group. Identify the side that had the OH, that's the carbonyl, and the other half is the Grignard. If we split off here, that means the group that we added had one carbon. So methyl magnesium bromide. And all the rest of this was our carbonyl. Our carbonyl compound had 1, 2, 3, 4, so it's a butanal with a methyl and carbon 2. And the pair would look like this. If we split on the other side, this was our carbonyl, so that's acetaldehyde, isn't it? And this part was our Grignard. Our Grignard, this was attached to magnesium bromide, and of course, acetaldehyde for this part.
Could you look at for just a second?
And our last one, another Grignard. Go ahead and do the simple Grignard exercise, split on both sides, give our 2 carbonyls and our 2 Grignard reagents. If we split here, our carbonyl compound, this was the carbonyl carbon, it was an aldehyde, and it had 1, 2, 3, 4, so it's butanal, isn't it? And this is simply an isopropyl Grignard. Finally, if we split on the other side, we are dealing with 1, 2, 3, so it's a propanal with a methyl group in carbon 2. And our Grignard had 1, 2, 3 carbons, so propyl magnesium bromide. Now, if you didn't get all of these, as we were doing them, they're in a nice set at the end. Print another copy or print those couple pages and try them again. A lot of this is reviewed from either 234 or from chapter 17-ish. There are only 2 or 3 new reactions in this chapter. But by this time, we have such a library of chemistry that we know that we can do all this stuff, right? Right. All right, I will let you know what the lab is for Wednesday as soon as I figure it out. Hello.
So, okay, C5H7 is CH3CH2O, which is this one.
That one would work.
Okay, there are two different CH2 groups,
Uh-huh.
so it would be this one as well as that one. And there's an isolated CH2.
You're missing a CH2 in
No,
this
no,
one.
this one.
Right.
Just this one.
The problem with this as a structure is you have an ethyl group in the NMR, don't you?
Yes. I thought it would be this one, the CH3, CH2.